It is both my privilege and pleasure to introduce our next speaker. He actually is a climate scientist. We've heard many people say that they're not climate scientists. Professor David Archer of the University of Chicago, he actually is a climate scientist. Officially, he's a computational ocean chemist. He's been a professor at the University of Chicago since 1993. I wish I could see the gentleman who hoped that scientists would have the same standards as accountants. I'd like to say that scientists do have a bit harder standards than accountants, I think. But Professor Archer has numerous publications in scientific articles. But in addition, he's written several books, and some of them for the lay public. And in fact, I would like to invite you all to the bookstore. There is an exhibit of some of his books there, as well as others, other books on climate change, if you get a chance to visit the Notre Dame bookstore, which is not too far away from here. So some of the books that he's written for the public include the Warming Papers. It's the Scientific Foundation for the Climate Change Forecast. The Long Thaw, which is also the title of his talk today, and the Climate Crisis. And he's also written some textbooks on the issue, global warming and understanding the forecast. So please welcome Professor Archer.
Thank you. Thank you. Is this good sound? Yeah, okay. So I wanted to start out very quickly coming to the defense of Phil Jones, the climate gate. We saw his picture in the last talk. He's not a bad apple. He's a good apple. He was smeared. Let me just show you. I wouldn't even bring this up except that you all seem to be interested in how weird it is to be a scientist in a politically charged environment. And so this is a great sort of case study or teaching moment or something. So what Phil Jones does is put together all of the weather station information to try to come up with what the average temperature of the Earth is doing from that data. And the urban heat island effect is a very real effect, and the problem would be if all the weather stations were in urban areas, and so you see warming and it's really caused by the concrete from the city, and you blame it on CO2, and that would be wrong. But lots of people have done these, putting together all the stations, and they're all getting the same results. So Phil Jones is the red one there, and NASA does this, NOAA does this, everybody, a little bit of variation, but the urban heat island effect has not turned out to be a significant pollutant to the global average temperature. So I don't know Phil Jones personally, but he, what I understand is that he was driven to near suicide by the sort of global scrutiny of this. He resigned as the head of the group that he was in until the investigations exonerated him and he was reappointed. It sort of feels to me like there but for the grace of God go I. So I want to sort of come to his defense there a little bit. So, so where are we? My presentation today is going to be kind of a counterpoint to one we heard from Ramanathan this morning, who told us about the importance of short-lived climate-forcing agents like methane and black carbon. And so I'm going to make I don't disagree with anything that he said, but I come to exactly the opposite conclusion sort of in the larger picture. So I'm going to explain to you where this comes from and what the issues are. So when you put CO2 into the atmosphere by digging it up from the ground, there's a sort of a multi-staged response as various processes take the CO2 out of the atmosphere. There's this very fast drawdown that takes a few hundred years as the CO2 equilibrates with the ocean. And, but that process doesn't take all of the CO2. So you can make an analogy to like a lump of radioactive material. If you had a lump of strontium-90, for example, has a 30-year half-life, it would go down following a curve. And by looking at the curve at the beginning here, you could extrapolate down on how this would sort of come into a landing, you know, sort of right about here, right? But the CO2 uptake is kind of like different isotopes, a lump of radioactive waste that has strontium-90 in it, but it's also got some iodine-129 in it or something like that. It has a different half-life. So the radioactivity that you measure now doesn't tell you. So the first stuff decays, you know, quickly, and then there's this leftover stuff that has a much longer decay time. So it's a more complicated function than just a single exponential curve coming into a landing at 0. So after the ocean invasion is done, there's still some of the CO2 that we put into the atmosphere stays in the atmosphere. If the ocean was infinitely big and it could take up all of it, then it would all go away by dissolving in the ocean, but that's not the case. And what happens to the rest of it, the last 20–25%, is that it goes away on timescales of thousands of years or something like that by chemical reactions with rocks. So that's what I'm going to show you, a couple of slides so you can understand how this works. So a lot of times you can, there has been this confusion in the climate science literature among climate scientists as well as you know, everybody else about this long tail of the CO2. And it comes from this table from the Intergovernmental Panel on Climate Change. So these are reports like the National Climate Assessment we heard about today, but that's a US thing. This is an international UN thing. And they come out every 4 or 5 years. They started in 1990, and there's a new one just coming out. The 5th one is just coming out. You know, it's in review now. They had this, so there are many technical chapters, and then there's summary for policymakers in the front, you know, for guys that are, you know, making the decisions but somehow too busy to actually, you know, read the real stuff. And it had this table, shows properties of all these greenhouse gases, CO2, methane, da-da-da-da-da. And one of the rows is the atmospheric lifetime, and they say 5 to 200 years. Well, so that would be the lifetime if this ocean uptake took the carbon all the way down to 0. But it doesn't. There's this long tail that's sort of not included in that. So basically, the long tail got sort of thrown out. The baby got thrown out with the bathwater here. By trying to fix a single number, it's like having a single decay time for that lump of radioactive stuff. You miss, you know, if it's not all strontium-90, but there's this other long-lived stuff, you miss that if you say it's got a decay time equal to the strontium-90. So the last report was in 2007, and this was rectified in that report. Actually, in the technical chapters, they always got it right. Just in these summaries for policymakers, they got it wrong. But as a result, everybody says the lifetime of CO2 in the atmosphere is about 100 years. In fact, if you were listening really carefully this morning, you heard that. But I'm going to show you why it matters that that's not the case. So here is some data from the geologic record that's very analogous to the global warming climate event that we are triggering now, without going into the details of how these tracers, so the carbon-13 to carbon-12 ratio of the CO2 that's saved in calcium carbonate. I'm not going to tell you why that's thought to be a tracer for CO2, just that it is. And then this bottom one is a tracer for temperature. So what you see, things going along kind of fine, and then that's like the fossil fuel era. The CO2 goes up, the temperature in the deep ocean goes up, and then the whole thing recovers on a time scale of 100,000 years. Not 100 years. If it was 100 years, we never would have seen it. 100,000 years. This is the result of a model intercomparison project. So models are, you know, they're complicated and they're hard to, you know, trust and evaluate. And one of the powerful ways that people who do this have figured out to shore them up, to assess and evaluate their reliability is to just get everybody together and everybody run the same thing, different models, see if you get the same answer. And if you don't, that means there's things that are done differently, assumptions that need to be challenged, things like that. This was a very unofficial, totally unfunded thing. We all just, by email, hey guys, let's all run our models. So all the models were subjected to a whole bunch of CO2 added to the atmosphere all at once. And then they were run for 10,000 years. And you see that none of the models are coming back to where the CO2 is what it was when you started. They're all coming in at a higher level than they started. And it's very simple chemistry, as I'll show you next. There's no wiggle room here. It wasn't widely appreciated until not too long ago. So the first stage is to dissolve the CO2 in seawater. And gases can dissolve in water, no problem, like oxygen, nitrogen, they do that. CO2 is special in that it does this chemical reaction with carbonate ion, the CO3 minus thing there. The CO2 and the carbonate ion come together and make those two on the right, the bicarbonate, HCO3 minus. So anything that has a chemical charge like that, the bicarbonate or the carbonate, is like a salt. It doesn't gas exchange to the atmosphere. So what the carbonate ion is doing is it's allowing the CO2 to hide, the CO2 gas to turn into a salt and sort of hide in the water. And if we ever get to the point that Ramanathan talked about this morning of scrubbing CO2 out of the atmosphere, it'll be done by something like this. You react CO2 with the base and it comes out. That's how they do it in submarines. Apollo 13, there's a great scene where they have to figure out how to get the air through some canister of base or something so that Tom Hanks doesn't asphyxiate before our eyes, which would be a horror just unimaginable. So the ocean contains about 50 times as much actual dissolved carbon as is in the atmosphere. So the first people to sort of think about this, Roger Revelle, for example, very famous sort of carbon cycle scientist, he didn't think that people could affect the CO2 concentration of the atmosphere. This is before there were real reliable measurements, sort of back in the 50s. Because he said there's so much more carbon in the ocean that it'll just mop up anything that we put into the atmosphere. And the ocean covers 70% of the Earth's surface. And so, it should be fast, which sort of makes sense. But most of the carbon in the ocean is not in the form of the carbonate ion, the CO3 the sort of anti-CO2, or antacid, you could even call it, that reacts with the CO2. So if you actually compare how much carbon there is in the atmosphere with how much there is in this carbonate in the ocean, it's a ratio of about 1 to 3. And so that sort of justifies why if you put a new slug of carbon in there, if it's not too big, you expect it to sort of spread out in that same proportion, about 1 to 3. So maybe 25% of the carbon you put in, if all that the Earth consisted of was, ocean water and then sort of a bed of Teflon or something like that, unreactive, you're just equilibrating between the air and water, you'd expect about a quarter of the CO2 to stay in the atmosphere and 3/4 to go in the ocean. That's fairly simple chemistry. So in these models, we try this experiment. No reactions with rocks, just between air and ocean. And how much is still in the atmosphere after it comes to equilibrium, after 1,000 years or a few thousand years? It depends a little bit on how much is added. If you add more, it tends to acidify the ocean, and it uses up the carbonate ion is what it does. So acidifying the ocean, another way of saying that is using up that carbonate ion, saturating the buffer, exhausting its capacity. And so then the airborne fraction is a little higher. But 25%, that's sort of about what they're all doing. Now, we'll see in a little while there were these amazing cycles in atmospheric CO2 during the ice ages. So we'll come back to that. But those are still not well explained or understood, but they are thought to have something to do with something about the ocean, biology, or temperature, or something affecting the way the CO2 spreads out between the air and the water. And so, you know, until we understand what was going on with that, leaves us kind of a little bit at a loss to predict the future with all that much reliability. So it's kind of a caveat there. The next stage, after the CO2 invades the ocean, it has acidified the water. It's made it more acidic than it was. The next stage involves calcium carbonate, which dissolves and neutralizes the acid. So calcium carbonate is what they put in Tums. If you got an acid stomach, you eat a Tums and it neutralizes it. It's exactly the same chemistry. And again, the CO2 winds up as this salt, this charged thing that doesn't evaporate to the atmosphere. There's no charged things in the air, just in water. So this process is a little harder to get our handle on how long it takes in that different models take, you know, they predict it'll take different amounts of time for the pH of the ocean to recover. But it's on the order of thousands of years. And then as the calcium carbonate dissolves and the pH recovers, that means the carbonate ion concentration is being replenished. And so that allows the ocean to take up yet more CO2. And so that pulls the CO2 down a little further, from about 25% down to about 10% of all that was ever released. And then the final thing is this beautiful thermostat mechanism that geologists have figured out, which explains this very uncanny stability of the Earth over geologic time. Carl Sagan published this problem called the faint young sun paradox, which is that the sun, as stars age, they get brighter. They put out more heat. And so if you were to take the climate of the Earth today and dial down the sun by 25%, which is what it would have been 4 billion years ago, the Earth would be in a deep freeze. And it would be for, you know, a long time until it got warm enough to sort of thaw. Or since we know there was liquid water 4 billion or 3 billion years ago, because there's sedimentary rocks that we can find, if there was liquid water then and you dial up the sun by 25%, we should be broiled. And yet, even though the heat source is increasing, the temperature of the Earth has been staying through these fairly narrow bounds. And that's thought to be due to this thermostat mechanism. So there's this grand cycle of carbon going into and out of the Earth. So we'll start with right here. This is calcium silicate. This is an igneous rock. So a rock that was formed from, you know, melted rock, like lava or magma or something like that, a crystalline igneous rock. And it dissolves in rainwater, and the constituents of it roll down to the ocean, where the calcium is combined with carbon to make calcium carbonate by critters, by coral reefs and by little planktonic organisms called coccolithophores that make little plates of calcium carbonate. So the calcium carbonate sinks to the bottom of the ocean, and the ocean crust is continually being recycled by plate tectonics, and so this calcium carbonate gets carried down into the Earth where it's hot, and if it's hot, the CO2 wants to be a gas again. You know, in a gas phase, it's free, and you put a lot of energy into it. It wants to run around. So the CO2 is cooked off of the calcium carbonate, and it degasses to the atmosphere from volcanoes and in the hot springs at the bottom of the ocean. They have a lot of CO2 in them. And sort of that completes the cycle. So what makes a thermostat out of this is that this step, the weathering step, where you dissolve this rock, it requires liquid water. And because, you know, the rivers are carrying, you know, each gallon of river water is carrying about as much dissolved rock as it can hold. So if you make more water running over the land, you'll dissolve rock more quickly. So the rate of water rushing over is a strong function of the temperature of the planet. There's much more runoff in the tropics on Earth than there is in the high latitudes, just because warm air can hold more water vapor than cold, and so you get more rainfall and everything. And then, in turn, the temperature of the planet is a function of CO2. So you end up with this thing. I tell my non-science major undergraduates in my class that it's like a kitchen sink where you turn on a faucet and the water starts running into the sink, and it sort of builds up in the sink because maybe your drain's a little bit sluggish. And then how fast it's going down the drain depends on the water level in the sink because there's more pressure if the water level is higher. So the water level in the sink finds the value at which it's dumping the water as quickly as you're putting it in there. And the CO2 in the atmosphere is the same way. It finds the value at which you're dumping carbon into the Earth as calcium carbonate from this weathering as quickly as it's coming out from degassing. So you have this kind of thing where if the CO2 was too low and the Earth was too cold, you'd have more CO2 coming out of the Earth than you are taking up, and so the CO2 concentration would rise, and it would tend to rise until it sort of starts to come in for a landing at that equilibrium, like turning on the sink. Or, apropos to our current conundrum, if you have too much CO2 in the atmosphere, you'll be weathering and consuming it faster than it's coming out from volcanoes, and the CO2 will tend to fall. So this sounds great that the Earth can clean up after us, but the trouble is that the time scale for this is longer than we'd like. It's sort of hundreds of thousands of years. We know it's got to be longer than that because the CO2 goes up and down through the ice ages, like I mentioned. And those have a time scale of about 100,000 years. So it's kind of like a thermostat in a house, and the sun is intermittently shining, so sometimes it gets hotter and colder, and the furnace is trying to regulate the temperature, but it takes time, and it keeps it's sort of fluctuating up and down above that set point. Excuse me. So here is the equilibrium amount of CO2 in the atmosphere as a function of time from all these models. I guess this is just showing you again that plot where none of them come back to zero very quickly. So there's not really new information here exactly. So what does this mean? Well, one kind of interesting, fun thing is if you burn a gallon of gasoline, you get a certain amount of energy from it. And then you put the CO2 in the atmosphere, and it blocks energy, trying to leave to space and causes the greenhouse effect. And you can figure out how much energy that carbon is trapping. So first, in watts per square meter, which 1 gallon of gas isn't going to change watts per square meter all that much, but then you multiply by the whole Earth, 1 gallon of gas isn't going to change much there either, because 1 gallon isn't very much. But then you add up over the lifetime of the CO2. So, 100,000 years, you've still got some percentage of that CO2 in the atmosphere. So you add up all of that energy over that time, and you can compare those two numbers. Anybody want to guess? It's a bigger number. It's actually, I looked it up and did the conversion. It's bigger than the first nuclear devices that they built in the Second World War, but it's not as big as the big hydrogen supers that they build now. So you burn a gallon of gasoline, and you're setting into motion you're setting off a small nuclear weapon, but fortunately it's a very, very slow one, so it's not as obvious as it would have been. So I want to tell you about how this works by comparing it with CO2. And I want to do this by showing you this little online web model widget that I just finished working on. And I want to actually take a moment here for a little sort of advertisement. I do this class for non-science majors. It's the biggest class at the University of Chicago. I have a textbook on it. I have all these online models that they do. And I also have, I've set it up as a MOOC, a massive open online class that anybody that wants to can register. You can watch all the lectures. You can take the tests. And if you get to the end, it'll print out a nice certificate for you that is free and will, grant you access to absolutely nothing. But it's there if you're interested. And so there are these online models, and so this methane versus CO2 one is the one I wanted to show. So let's compare a slug of methane with a slug of CO2 in how they react. So methane goes to the atmosphere and it gets oxidized, gets turned into CO2 on a time scale of about 10 years or something like that. While it's still methane, it's a much more powerful greenhouse gas than CO2 because there's more CO2 in the atmosphere than there is methane. And so the absorption bands are more saturated for CO2, which just means that the bang for your buck kind of goes down. You know, if you have a gas that has that didn't exist at all before, and you put some into the atmosphere, it has a huge climate impact. So that was where I first, that was one of the first things I read from Ramanathan, the guy who was here this morning. He wrote this beautiful paper about how a molecule of Freon has as much greenhouse forcing as 10,000 molecules of CO2 because of this band saturation effect. It's not as strong between methane and CO2, but it's still strong. As you can see from, here is the temperature response from that CO2, and here's the temperature response, the red one there, from the methane. So you can see you're getting a lot more bang from the methane. So let's try to tweak this a little bit by seeing how much CO2 is equivalent to the methane. And it turns out that about a factor of 40 means that the initial warming that you get from the slug of CO2 is the same as from the methane. So methane is 40 times as powerful as a greenhouse gas is kind of the conclusion that people would take from that. But let's zoom out now in time. We'll look at 500 years and see what's happening. So here's the methane concentration. It drops within a few decades because it's reactive gas. Here's the CO2. It's only beginning its trajectory downward. It's got to go all the way down to 280, 278 or something, so it's way off of this plot. The methane, all right, so the amount of greenhouse forcing, they call that radiative forcing. It's in units of watts per square meter. And the forcing from the methane and the CO2 are similar at the beginning, which is why they both had the same warming effect in 10 years. But then the methane goes away right away, whereas the CO2 is sticking around. If we asked what the temperature of the Earth would do if it could warm up instantaneously, the equilibrium temperature from those greenhouse gases, they would be sort of about the same initially. But the thing is that the Earth takes a long time. It takes hundreds of years for the temperature to completely respond to the greenhouse gas concentrations. And that's because the ocean holds a lot of heat. So if we were living on Mars, the climate of Mars, if you change the greenhouse gas concentration with no water, would relax, would equilibrate in a couple of years. So you run a climate model on Mars, it's much less of a computational job. Whereas on Earth, it takes a long time to heat up the ocean, 1,000 years, something like that. So the equilibrium temperature is not what happens. What happens is a sort of time-dependent temperature. And so now you can see that that initial warming from the methane just kind of didn't pan out because the methane went away. So you sort of deliver a body blow to the temperature of the ocean. You dump some heat into it, and then it takes a few hundred years for it to kind of recover from that. But the warming is all isolated to the very beginning here, and then that's it. Whereas the CO2 sticks around for an amount of time which is long compared to how long it takes for the Earth to warm up. And so the ultimate warming you get is tabulated here in the sort of degree years of warming. And so if we zip back to our short time horizon, they look like they're about the same, right? But then as we go ahead in time, 1,000 years, 1,000,000 years, see the CO2 is finally going away, and you see the CO2 is a much stronger greenhouse forcing agent on that sort of long time scale than the methane. Methane is just gone. Another fun fact is that the band saturation effect, which is the reason why as you get more and more of a gas, it's sort of less and less sort of bang for your buck. What that does is it tends to smush down the peak and emphasize the tail if you're looking at the temperature response instead of the actual CO2 concentration. So the top one is a trajectory of CO2 concentration over 500,000 years. You get a spike, and then, oh yeah, there's this long tail here, but easy enough to sort of forget about that, throw that baby out with the bathwater. But you look at it in temperature, and it tends to de-emphasize the peak and makes the tail much stronger. So, you know, if you start looking at 1,000 years or something like that, it basically, you get the impression that CO2 changes climate forever. It just doesn't go away. It accumulates like old magazines. It just doesn't ever go away. So I totally agree with Ramanathan that what we need to do ultimately is scrub CO2 out of the atmosphere, because we're going to overshoot and we're going to have to pull back, and it's just going to have to happen. You heard it here first. So one of the, there are aspects of the climate system that depend most strongly on the long tail. Well, it's a philosophical issue. I mean, we're all going to be dead before any of this happens, and so, you know, maybe we don't care. That's, you know, if you want to take that position, I can't argue against that. I would say that one of the main reasons why I personally am uncomfortable about nuclear energy is that you have to safeguard this nuclear waste for 10,000 years, and I just don't trust, you know, it just doesn't seem like a good thing to burden, you know, the next 10,000 years of the Earth with this obligation. And if, you know, they were to go to breeder reactors and therefore burn out all the heavy, the long-lived isotopes and make things that go away in 100 years, even though I won't live to see 100,000 or 100 years from now, I would be more comfortable with the 100-year sort of solution. And I feel the same way about the climate. So if you'll grant me then the indulgence to be concerned about things that'll happen long after we're all, you know, re-entered into the carbon cycle, there are parts of the climate system that are most strongly impacted by this long tail. And one of them is sea level. So this is a plot of changes in sea level and global temperature from the geologic past. So here's today in the center there. Average temperature there is about 15 degrees centigrade. Here's the last ice age about 20,000 years ago. It was only 5 or 6 degrees colder on a global average during the last ice age. You know, it looked different from space. The planet would have looked different. It was a massively different climate, and that was only about 5 or 6 degrees centigrade colder. So you can sort of use that to calibrate the forecasts for the, you know, 3 or 5 degrees in the future. It's like a fever, you know. 1 degree, I've got a fever of, you know, a 100-degree fever. It doesn't sound, I'm 2 degrees hotter than I should be. It doesn't really describe, you know, what it's like to have a fever. And it's sort of the same way with these temperatures. So during the last ice age, there were these huge ice sheets, and sea level was 120 meters lower than today. There was a time before that when there was much less ice in Greenland, about 3 million years ago, called the Pliocene. And it's a little dodgy what the sea level was there, but it's thought to have been sort of 10 to 20 meters higher than today. And then if you go back further in time, most of Earth history, actually there's no ice sheets at all. We live in a time that a geologist calls an ice age, actually, even though we think of the ice age as being 20,000 years ago when there were mammoths and all that. But just because there's the ice sheet in Greenland and Antarctica, that's unusual. Most of Earth history, there's no, it's sort of a hothouse climate, and you don't have ice. And so to go back to a time like the Eocene, when it was a hothouse climate and there was no ice, now it's really hard to pin down the sea level because the land surface itself is kind of, you know, moving up and down, all that geology stuff. But today there's enough ice to raise sea level by about 70 meters. So that's the sea level change to get to that hothouse climate there on the right. That would be how much sea level rise there would be if there were, you know, current present day geometry of the continents. So, you know, there's a world of complexity in this, but you can also just draw a line and connect the dots. And on that plot now, we can put the forecast for the year 2100 of the temperature change, sort of 3 degrees or so. And then the sea level rise for the year 2100 is projected to be about 1 meter, half a meter, something like that. It's totally not on that plot from the past. Excuse me. And the reason why it's not is because it takes longer than 90 years for the ice sheets to come to equilibrium. They take thousands of years to melt, hopefully. But since we know that the CO2 is going to stick around for thousands of years, no problem, the long tail is there, the ice sheets have plenty of time to respond. And if they do, we're talking about tens of meters of sea level change in response to the CO2 that we emit. Granted, not by the year 2100, because they're slow and it won't happen on that time scale. But it's kind of like you see somebody standing at the edge of a cliff and they're looking despondent and you want to help them out. And so you say, hey, if you jump in a half a second, nothing bad is really going to happen to you. And that's because it takes 2 seconds to fall all the way down to the bottom of the cliff. You're talking on the wrong sort of time scale for the process. We burn the CO2, sea level is only going to go up by 1 meter or 2, but that's like the wrong time scale. It's the human time scale, so it's a time scale that we are intrinsically interested in, but it's not the time scale for the physics of the process at all. Totally wrong. So if we sort of do the math, let's say we were to burn all of the estimates, these may be wrong, but the traditional estimates for how much fossil fuel is available are about 5,000 billion metric tons of carbon, mostly in the form of coal. And it would take probably more than just this century to burn that coal kind of in business as usual. But that's how much there is. If we don't leave it in the ground, that's how much there is thought to be. And so we run that through that graph and say that we're to raise sea level by 20 meters eventually. I added up, that's 3.5% of the land area of the Earth. And people like to live close to sea level. River deltas are very fertile. River deltas in China are very populous, for example. So it turns out that that area is home to 10% of the world's population, which seems to me like it's saying we're throwing away 10% of the carrying capacity of our planet in order to indulge in this fossil fuel. So if you divide it out, it turns out that it's about this much area of land that's lost eventually, maybe after 1,000 years or so, but eventually, for every gallon of gas that we burned. So I burned 2 or 3 to get here this morning, and I got to go home again. Or you do it another way, 1,000 square feet per year per American. That's how much land we are permanently sacrificing by indulging in this. Another thing I worry about on the long time scale is sort of carbon cycle feedbacks. So this is a map of soil carbon, and you see there's lots more up in the high latitudes. That's because it's frozen. It's like if you put a ham sandwich in the freezer, it'll be there, 2 years from now or whatever. You put it on the counter 2 years from now, it's gone. So the carbon that that's falling to the ground in the Amazon isn't accumulating in the soil because it's all decomposing so quickly. But up in the high latitudes there, especially places, just in the high latitudes there, you see lots and lots of carbon that's frozen into permafrost, which is in the process of melting. And there's enough carbon there that it could be a significant amplifier to the amount of carbon that we put in, like matching funds or something like that. We put in a couple thousand gigatons, and hey, the carbon will, the soils will kick in another 1,000 gigatons or something like that, kind of amplify what we do. It's a possibility. Another such thing is methane hydrate in the ocean. So methane is a gas, and but it gets trapped by these weird water ice crystals called hydrate. This is a structure that Linus Pauling actually discovered the water forms kind of like soccer balls, kind of a cage, and it has to have gas molecules inside some fraction of those soccer balls. They're not chemically bonded, so it doesn't matter what gas, but just something to sort of rattle around in there to kind of make it stable. And it just turns out that over geologic time, pretty large amounts of methane have gotten frozen into these structures in sediments at the bottom of the ocean, sort of around the edges of the ocean where there's more carbon kind of flowing around. And it's not something that's going to just blow up all of a sudden, because it takes a long time to warm up the water of the ocean, and then it takes the heat has to diffuse down into the sediments to melt this methane, and then the methane has a real hard time getting out to the atmosphere. It might go to the ocean and then slowly kind of leak to the atmosphere as CO2 or something like that. So it's not something to worry about this year or in the coming decades. But in the fullness of 1,000 years into the future, there's a lot of carbon down there, and it seems like it could, well, what we're getting is that as you warm it up, the steady state amount of methane in the ocean should be much lower. How long it takes to get to that value is kind of like unknown still, but it's a potentially big feedback, thousands of gigatons of carbon possibly. There's evidence for a positive carbon cycle feedback through from data from the ice cores. This is ice core concentrations of CO2 from the last 1,000 years, and there's this sort of period of drop here during a time called the Little Ice Age. This is not the big ice age with the mammoths and all that. This is just sort of a period of time from about 1350 to 1750 here, when it was kind of colder than average in Europe. It was thought to be caused, there was a period when there were no sunspots, kind of right in the middle here, so this is thought to be caused mostly by sort of dimness of the sun, basically. But the point is that the CO2 concentration went down during this time too, because the ocean's colder gases can dissolve more easily in cold water, and so this was a positive feedback. The sun got colder, and then the CO2 said, yeah, I'm going to make it even colder. And then, of course, the biggest carbon cycle feedback are these glacial interglacial cycles. So we have, here is time going this way, and the ice volume on Earth is well, here's, I guess this is upside down. This is actually sea level as driven by the ice. So we're at a time of high sea level today because there's not as much ice. Here's the last ice age 20,000 years ago, and sea level was 70 meters lower because of all the Laurentide ice sheet that was here and caused, dug out Lake Michigan for us and all that. Here's the last interglacial time, and sort of going back through time. And the weird thing is that the CO2 concentration in the atmosphere is following suit, and it's just a gorgeous correlation. You just don't get this good a correlation very often in the natural sciences. So, and the trouble is that everything we try to do to ocean models to make them do this, it's hard. You can clobber an ocean model every which way from Sunday, and to get it to change the CO2 that much, you have to do everything just right. You have to have, we call it a CO2 stew. You have to have everything lined up in just the right way to make it get that full amplitude. And this doesn't look like a whole bunch of things acting in concert. That would seem like it would give chaos. This is so ordered that there's something simple that we're not getting. But the issue, I mean, that's an issue for geologists. The issue for us is, well, today, the carbon cycle is actually helping us out, right? Because we put CO2 in the atmosphere, and but it's dissolving in the oceans, and it's being taken up by trees. And so actually, the rate of CO2 rise in the atmosphere is only half as big as it would be if the carbon that we put there was staying there. So half of the carbon that we're putting in there, the natural world is mopping up for us. It's dampening down then the CO2 change and the climate change. It's acting like a negative feedback. It's helping us out. But in fuller geologic time, it seems to me very plausible that it could reverse and amplify climate change by doing something like it did in the past. These changes all took place on timescales of 1,000 years or longer, which is how long the ocean and the atmosphere communicate with each other. So I'm not worried that this is going to happen, overnight, but I'm worried about it in the fullness of the long tail of the fossil fuel CO2. So a few slides on this, just because it's cool. How are we doing? What am I? 3:30? Okay. This is how the orbit of the Earth varies through time. So here's today, and here's past, and there's these three components of the way the Earth orbit varies around the sun. One is the precession of the equinoxes, which is like a top sort of spinning like this. So here's the sun, and sometimes the winter is winter would be the northern hemisphere pointing away from the sun, would be at one part of the orbit, and other times it's at another part of an orbit. So it's sort of like that. The obliquity is how much it's tilted, and the eccentricity is how circular or elliptical the orbit is around the sun. And it turns out that when the sunlight gets dim in the northern hemisphere summer, that's when the climate of the Earth responds, through the ice ages. So the top plot is how bright the sunshine is at 65 degrees north on the summer solstice. So northern hemisphere is important because that's where the ice sheets are that come and go through the ice ages. And summer is important because that's when you decide whether to melt the ice back or to keep it and continue to grow an ice sheet. So whenever it drops below that critical trigger, the amount of ice, see we're going this way in time now, the amount of ice just sort of spikes upward. So this is the part of the glacial cycle that we understand the best because it's starting from an interglacial climate, which is what we're in today, and we understand that. Once you launch and nucleate the ice sheet, then we can't really figure our way through the cycle very well. But this one stage, nucleating an ice sheet, we can do that, it seems to me. And they can do this in a model. They dial down the intensity of the sun in the northern hemisphere summer by changing the orbit, and there's no ice, and all of a sudden you pass this trigger sunlight intensity, and boom, you get ice, and it grows more, and then it sort of stabilizes itself for a while as you warm back up because the ice reflects sunlight back out to space. It exists, and so there's a hysteresis, which is interesting but not really important to us. What's important to us is that if you change the amount of CO2, it changes the value of that critical trigger at which you start to nucleate the ice sheet. So we get this out of the model. But it also makes sense that if you have more CO2, you've got to cool down the sun in order for this ice to form. So if you take the, here's now putting it all together. Here is atmospheric CO2 through the past 400,000 years from the ice core. So that was that sawtooth record that looked so beautiful before. Now it's all squished up because we have to make room for the fossil fuel peak, which is here. So green is if we added no carbon. There's 1,000 gigatons. That's basically business as usual to the end of the century. 5,000 gigatons is burn all the coal. And then here is the sunlight intensity, and the green is the critical trigger at the CO2 value that is natural, but the trigger moves as we change the CO2. So we actually push the trigger way out of reach of these orbital variations. And the cool thing is that the orbit of the Earth is approaching near circular at the present. So the last time the orbit of the Earth was nearly circular, an eccentricity of 0 here was 400,000 years ago. Happens every 400,000 years. And that's where we're headed. What that means is that if the orbit is circular, it doesn't matter where the northern hemisphere summer is around the orbit. If it's all the same distance from the sun, it doesn't matter. So that means that the variability in the forcing that you expect is going to be sort of at a minimum in the next sort of tens of thousands of years, just at the time when the trigger to cross is pulled way, way, way out of range. So for what this is worth, this is a very simple model, but I know you're curious, the trigger was getting real close in the natural world in a couple thousand years. It just comes up and grazes that green line, but it doesn't really decisively cross it at all because the orbit is circular, so there's no variation in the intensity. And you see that it starts to cross it more decisively again, sort of tens of thousands of years from now. So the last time it was circular, the orbit, the interglacial lasted for 50,000 years. Probably would have this time too, but we have the capacity to knock it out of whack until the end of not this period of circular orbit, but the next period of circular orbit, 400,000 or 500,000 years in the future. So I'm not arguing for the ice age, can't bleed for the ice age, but it is amazing to me the potential we have to modify the climate of the Earth throughout geologic time. So just to sort of wind up some more about CO2 to leave off, it turns out it doesn't really matter too much to the peak temperature that the Earth will get how quickly or slowly we burn the carbon. The thing that matters is how much we burn before we finally stop. So if you burn it quickly, the peak comes more quickly. If you burn it slowly, it comes more slowly. But the temperature at that peak just depends on how much has been released. There's some things that sort of cancel out to make it this way. So they estimate that if we burned 1,000 gigatons of carbon total, we'd start to get close to crossing this turning point temperature change of 2 degrees centigrade, which is warmer than the Earth has been since long before there was, civilized humanity, warmer than it's been in millions of years. So 2 degrees is no picnic, but kind of just a turning point. Beyond 2 degrees, things start to get even scarier. And 1,000 gigatons would get us there, and we've already burned about 500. So this is what the emissions of carbon are doing. They are rising. That's called business as usual, rising a couple of, 3% a year or something like that. If we want the total amount that's ever released to come in at 1,000 gigatons, if we started to ramp down now, we could make cuts of a few percent per year. And then, this thing would sort of glide down to a landing. And if you take the area under the curve, that would be 1,000 gigatons. And so that would put us right at the brink of that. If we wait, the longer we wait, the more of a crash program we have to do to keep the total amount under that. And, every percent per year cut that you try to do costs money because it's, power plants and things like that. So it's like assigning a term paper to your students or in your classes where the deadline is, say, Monday for a 5-page paper, but you can turn it in on Wednesday, but then it's 7 pages, or you can wait till Friday, but then you got to write 20 pages. It's like that. Tell them that, they'll understand. So the trouble is that there are all these different things. Carbon is much easier to cut black carbon that Ramanathan was talking about, or maybe methane. CO2 comes from everything that we do. And so there's no simple one thing that will fix the problem. And so they talk about wedges. So going from business as usual to some sort of stabilized thing requires is the difference between this much emission and that much emission. And there's no one thing that can do that, so they cut it up into pieces they call wedges. And then, so this paper was 2005. They said that they wanted 7 wedges to stabilize CO2, and they listed 15, all of which are available with currently available technology today. So, better gas mileage in cars, nuclear energy, windmills, stuff like that. You just need to pick 7 of those things, and it can be done. And then another perspective on fossil fuel, it's hard to think about not being able to fly to your vacation or whatever, but really the big issue isn't oil or natural gas. Really the big issue is coal, because 90% of the fossil fuel is coal. And it seems to me they could go build new power plants that aren't coal, and we would never know the difference. It'd be like building a new stadium. Maybe there'd be some tax levy or something, but it could happen. If there were just no more coal on the planet, you know, if we're wrong about how much coal there is and we just suddenly run out, we wouldn't have to go back and live like the Flintstones. It would be a business opportunity. It would be no problem. The only problem is making the decision to leave it in the ground. So the impact of releasing CO2 isn't just 100 years. It will last basically forever. It will cause sea level rise ultimately to be 100 times greater than what you've been told from the IPCC, because we just won't be around personally to see it, but that's what we are setting in motion. And then the carbon cycle also has potential to be an amplifier of climate change on these sort of long time scales. So, you know, if I could make a choice between cutting black carbon and methane and cutting CO2, I would choose CO2 instantly, no question about it. I think Ramanathan would probably say the same thing. He was very careful to say, you know, keep our eye on the ball of CO2, but also do these other things, and I totally agree with that. But CO2, it's the CO2. Don't forget, that's the thing. Thank you.
I just want to clarify from you, when you said that the temperature increase is 2 degrees Celsius, that's not on a global scale, is it?
Yeah, that's what I was talking about.
Well, is this an average temperature increase? Because if you look at the whole globe, then you will have some areas where you have higher temperatures and other areas will have lower temperatures.
Yes, so, you're absolutely right. For example, land has higher average temperature than the global average, and ocean has less. So being land-based creatures as we are, 2 degrees doesn't really adequately represent what we would experience, because the land warms actually more. If that's what your point is, you're absolutely right.
So when estimates say that the temperature will increase by, say, 5 degrees Celsius by 2100, how do you read this?
Well, so there's a really, I have my students read a book actually by a guy named Mark Linus called 6 Degrees. It has 6 chapters in it. Chapter 1 is about climate impacts of 1 degree sea warming, which is basically where we are now, and then 2, 3, 4, 5, and 6 degrees of warming. And by the time he gets to chapter 5, for 5 degrees warmer, he's hysterical. And it's almost hard to read because it's so shrilly depressing that you sort of have to I tell my students to sort of pace themselves. 3 degrees is sort of where rainforests start to come out and ice sheets collapse. And then, you know, by chapter 5 and 6, the potential climate impacts are just massive.
Yeah, one last question. If we are to use other alternative sources of energy, like hydrogen, ethanol, solar energy, wind energy, what do you think about these sources in terms of applications? And would they save us some of the fossil fuel burning?
What I showed was kind of a perspective for the next coming decades to kind of the year 2050, and the story was that we could get where we need to go with existing technology. But if you look further than that to, say, the year 2100, there were a series of papers by a guy at NYU named Marty Hoffert, who put together the constraint: we can only emit this much carbon, and the energy needs are growing, and extrapolating those forward. And then the difference between those is a required carbon-free energy source. And to get to the year 2100, really nothing that we have today can do that. So I was at this meeting that they put on, and there were all these beautiful, really luminary talks about different strategies that could actually scale up to that kind of a thing. One of them was to build solar cells on the moon. So you make them out of the lunar regoliths. You don't have to lift them all up there. It's better than having them in orbit and then beam the energy back to Earth by satellite. That could scale up. Another one, actually solar thermal, they claim, and that's a little bit less, you know, pie in the sky. Solar thermal is where you use magnifying to use sunlight to boil water and then use that steam to generate electricity just as if you'd used coal in the first place. They say that could scale up to the needs by the end of the century. But basically what we're talking is there's some grand, massive challenge. But 100 years is a long time, and if you look at what energy sources have been in the last 100 years, you know, we haven't been living our exact lifestyle for 100 years either. In this country, you know, they burned wood until they started to run out of wood, and then they burned coal. You know, and so there's these peaks of energy sources that kind of come and go over the decades. So the fact that, you know, somebody has some homework to do in order to keep the lights running by the year 2100 doesn't really alarm me too much, because we're such an innovative species that if you can make money doing something, somebody will do it. I think the trouble here is the tragedy of the commons, you know, persuading ourselves to step back from the fossil fuel and go a different direction. It's a decision-making problem, I think, more than a technical one, my opinion.
So, excuse me, the next part is questions and answers generally. So please, only if you have a specific question to David Archer.
You do have a specific question to David Archer.
Okay.
So I didn't, except for one, I think there was one slide where the word biology appeared.
Where,
And
sorry?
it was one of your slides where the word biology appeared.
Yes, a good one, a good slide, right?
Yeah, it was a good slide.
Yeah.
And you know, I was quite interested because, and I really don't know the answer to this question, because you're talking about very long time scales and the inorganic carbon cycle and the carbon in rocks and so forth.
Yeah.
And yet, the fact that we have fossil fuels is a consequence of elevated rates of primary production of biological activity in the ancient past.
Of preserving the organic carbon, yes, that's true.
Right, exactly.
Yes.
That's the reason we have fossil fuels, right?
That's also the reason why we have oxygen in the atmosphere.
Correct. So, so I just wonder if the numbers that you've given us in this sort of very, very long view, where does biology fit in that? Is there anything that could be completely different than what you've suggested if we were to introduce some sort of understanding of how biology might change in response to this?
Well, if the way the biology impacts the carbon cycle in the ocean is by a process known as the biological pump, where the plankton grow in the surface and then they sink down into the deep and they decompose, and so it carries carbon down into the deep. So if you could somehow kill all the biology in the ocean, CO2 in the atmosphere over the next 1,000 years would rise. Or if you could make it, you know, go faster, strip out the fertilizers, the nitrate and the phosphate at the surface more efficiently, in theory you could pull the CO2 in the atmosphere down some. And they talk about, there is talk about doing that as a solution to global warming, as a way of getting CO2 out of the air, which I've done, lots of people have done model studies and found that this doesn't work because it takes too long for the atmosphere and the ocean to equilibrate. So if you could fertilize the ocean for 500 years, you might start to get somewhere, but throwing old Volkswagens, you need iron to fertilize plankton. You throw iron in the ocean, you get this plankton bloom. So a lot of sort of defense contractors were getting all salivating, thinking about this eternal contract to go grind up old Volkswagens and put them in the Southern Ocean. But I don't think it would affect the CO2 trajectory in the near term very much at all. On the longer term, I take the ice ages, the glacial interglacial CO2 cycles, as a real cautionary tale, because we can't explain them. And so, you know, can't explain the past, can't really predict the future to that extent.
One quick question. You're talking largely coal as a basic source of the carbon, but what role, if any, do you see in the short term for the natural gas? We're getting a lot of the unconventional natural gas.
Right,
Just
right.
what
Yeah, it's
are
all
your
in the
thoughts?
news. Yeah, so there's fracking that brings, you know, makes available gas deposits and also oil that were not before. Some of these deposits, like the Bakken shale or some of these other Marcellus shale, they hold hundreds of gigatons of carbon, but I guess the efficiency with which they think they can extract that is generally sort of low, like on the order of 1 to 10%. So we're talking about amounts of carbon. You know, if they build Keystone, there's 700 gigatons of carbon up there, but they can only get 10% of it. And so that's like 70 gigatons of carbon, which is, you know, you can stack that up against our total allotment of 1,000 that we've burned 500 of. It kind of simplifies the regulatory picture when you have that slug thing, because there's only so much you can do, and that's it. So I think those are, in short answer, sort of a short-term, they've perturbed the energy balance. They made gas less natural gas less expensive than it was. But those wells don't go for very long. And so I don't expect that to be a real big game changer. There's also controversy about the total amount of coal available. The traditional estimate, like I said, has always been about 5,000 gigatons, but there are some people now who are arguing that the amount of available coal might only be 1,000 or something, which would be great news if that's true. I don't know if it is or not. But it all depends on technology and economics. So it's sort of flexible in that regard.
Let's say